In this lesson, we're going to take a look at the lines in two space like we did in the last lesson. Okay, we'll review those, and then we'll carry on and we're going to take a look at another line in two space. We've got one more, I guess, form of a line in two space that we can take a look at. But to start off with, as we did in the last one, we looked at vector equations. Okay, an example of a vector equation. We've got our vector equaling our known vector to us, and let's say it's just 3, -4, and then we have our direction vector with our scalar beside it, or our parameter, and we're looking at something like 2, 3. Okay, so what we know from here is that this is our direction vector. Okay, similar to slope, right? It's a direction, gives us the direction we're going into. All right. We also know that the point 3, 4 is on the line. Okay. When we change our parameter t, we can find all the points that are on the line. Okay. When we get to our parametric equations, our parametric equations are for the components. So we have, in this case, would be x equaling 3 plus 2t, y equaling -4 plus 3t. Okay. And finally, we looked at our symmetric equations. Okay. The symmetric equations, we isolate, solve for t. Since t is the same, we can have them equal each other. In this case, the left side and right side. So we have that x minus 3 divided by 2 will be equal to y plus 4 divided by 3. Okay. So that's what we have from the last day. All right. What we could do with these, I'll put these over on this side. If we take a look at determining the angle between lines. Okay. So again, in 2 space or in 2D, all right, if the direction vectors are not scalar multiples, then the two lines intersect. Okay, so if direction vector is not equal, or not equal to some scalar multiple, for k being some scalar, all right, then we could say that line 1 intersects with line 2. All right, so that's what this means, what we just set up above. All right, so what we can do with that is we can determine the angle. Oh, we already said that. We want to determine the angle between the lines. We can say then the angle between L1 and L2, the two lines, is equal to the angle between the direction vector. Okay, so here's an example. We'll take a look at a simple example here. Let's say we have an L1 and we've got x well, let's just use the one we had before. We've got x minus 3 over 2 equals y plus 4 over 3. And let's say L2 is x plus 1 over 3 equaling y minus 4 over, let's say 5. Okay, so what we have here, what you notice is the direction vector of M1, okay, or of line 1 is 2, 3, and the direction vector 2 is 3, 5. They are not scalar multiples, all right, which means they intersect. L1 intersects L2, all right, so we can then determine the angle between them, and for angles, remember, we use the dot product, all right, and so we know that cos theta is equal to the dot product of the magnitude of the M1, right, dot M2 divided by the magnitudes, the product of each magnitude, right? So let's take a look. M1, M2, 2 times 3 is 6, plus 3 times 5 is 15. Magnitude of M1, 4 plus 9 is 13. 9 plus 25 is 34. So then we have that theta equals the cos inverse of, what's that, 21 over 13, 34. Okay, then we can go to our calculators. We have cos inverse of 21 divided by the square root of 13. No, square root of 13 times the square root of 34. And it looks like we have a nice small angle, 2.7 approximately. Small little angle. Okay, so that's how we find our angles. All right. Now, the last thing, okay, or the last equation that we're going to take a look at is called a scalar equation. Okay, I'm going to show it to you over here. The scalar equation. All right, this is the scalar equation in two space. Okay, so we're taking a look at two dimensions. All right, and what we're going to try to do in this one, it's going to be different from the other three. The other three are using the direction vector, which basically is kind of like it's parallel to the line, right? It can be put on top of the line, goes in the same direction of the line. A scalar equation looks at a normal vector to the line. So what we've got here is, if we take a look at any line, all right, and what we have for any line, let's say is, is we have the point A that's on the line, A1, A2, so it's a known point, we know this, right? And then we'll take a look again at any P that's on the line, like this is any P itself, right? It can change, all right? If we're looking at, or if we have rather, a normal vector to the line, that means it's perpendicular to the line itself. So let's just assume we've got a normal vector here. We'll say that this is n, okay? N is going to be, let's say it's capital A, capital B, all right? Normal vector, 90 degrees here. What we know about this then, because it's perpendicular, again, perpendicular, what do we think of? Now that we're in grade 12, we think that the dot product is 0, right? So we know that the normal vector dotted with, now what we're going to do is we're going to take the vector from our known point A to any point that's on the line. Okay, so to AP, we know that's going to be 0. All right, so we're just going to substitute some values in. The vector n is AB. The vector AP, all right, we know is x minus A1 and y minus A2. We know that equals 0. Okay, so we perform the dot product. We have A times x minus A1 plus B times y minus A2. That equals 0. Use the distributive property. AX minus AA1 plus BY minus BA2 equals 0 there. With a little rearranging, we can just say AX plus BY. We have minus AA1 minus BA2 equals 0. All right. Now, in this case, to clean it up, what we notice is that negative A times A1 minus B times A2 is a scalar itself. All right, these would be known variables. So what we're going to do is we're just going to let this value, the A1 minus BA2, be equal to C. And look what we end up with. We have AX plus BY plus C equals 0. All right. This is the scalar equation of a line in 2 space, and it looks oddly familiar, right? Standard equation of a line that we learned in grade 9. Okay, A and B, the capital A and B in this case, is the normal vector that we have. All right. The C value completes the equation. It makes the equation true. All right. So we can use this by just stating or just trying to figure out what C is to make everything equal to 0. All right. Let's say, for example, if we let our normal vector be equal to 2, negative 6. Actually, let's not use negative 6. Let's just use negative 7. All right. And we have the point 3, 5 on the line. In order to come up with the scalar equation of the line, okay, we know that we need to come up with this, where everything equals 0, right? So we substitute the values in. We have 2 times 3 plus negative 7 times 5 plus C equals 0. So 6 plus negative 35 plus C equals 0. We have negative 29 plus C equals 0, so C is equal to 29. So that means our equation of the line, the scalar equation, is 2x minus 7y plus 29 equals 0, right? Again, if we substitute in the 3 and the 5 for this x and this y here, we know we're going to end up with negative 29 because we did it right here. So negative 29 plus 29 is equal to 0. Okay, so our equation, that's how we find our scalar equation of a line in 2 space. Okay, now I've got a couple of examples that are over on the end of here, so instead of rewriting them all out, I'll just show you what we've got there. Okay, so let's finish this off. Show that 2 lines in their scalar equations are parallel and non-coincident. Well, lines that are parallel, if we had them in grade 9, right, their slopes needed to be the same and their y-intercepts were not the same. Well, in the scalar equation here, now that we're in grade 12 and we've got this, what we need to figure out is that the normal vectors are scalar multiples of each other, right? We could say that the normal vectors are scalar multiples of each other, right? And that gets it to be parallel, right? Okay. And the C values have to be the same scalar multiple of each other, all right, for these to be the same line, right? If the C values were not scalar multiples of each other, but the normals were, then we know that they are basically parallel. Okay, get rid of that, and we make it parallel. So it's the conditions we're looking at. Right? So in this case, this is what we're looking for in A. So what you can do is you can say, all right, well, L2, let's just do it up here. L2 is actually 2 times 3x minus 4y plus 6 equals 0, right? You can see from this then that n1, actually we can say, yeah, n2 rather, is just 2 times n1, but C2 is not 2 times C1. Okay? So that's how you prove the first one. They're parallel, non-coincident, meaning they're not the same line. All right, we have that. Okay, you can always pause this to write this down and then move on to the next part. So finally, in B, if we take a look at it, for what value of K are the two lines perpendicular? Again, perpendicular, what does that mean to us? It means that the dot products are going to be 0, right? If the lines are perpendicular, then the normals are perpendicular, right? So the dot product of the normals would have to be 0. So we can just quickly say, okay, well, we've got K4, dot that with 3, -2. That has to equal to 0. So 3K minus 8 equals 0, or K is equal to 8 over 3. Okay? When you take a look at these questions here, remember you're looking at conditions too when they ask you to prove certain things, like they did in example 3 here. What conditions need to be met in order to prove what you need to prove? Okay? Good luck with these.